So let's finish up section 2.3. So we've looked into finding delta values for given epsilon values when we're dealing with functions of the form mx plus b. The graphs are straight lines. Now, if we deal with functions whose graphs are not straight lines, things become a bit more complicated. Let's illustrate it with example 2.3.4. They give us an alleged limit, and we'll go through and confirm that, in fact, their claim is correct. Okay, but the function we're dealing with this go-round is the square root of x minus 1. As you know, square root functions have graphs that are half of parabolas. And we'll actually look at the graph and extract information from the graph for this one. For the limit as x approaches 5 of the square root of x minus 1 equals 2. This is true, if you like, by the root rule. The function x minus 1 is positive, close to 5. I plug in 5, I get out 4, so it's close to 4 when x is close to 5. So the square root function is receiving inputs that are not close to 0. So we don't have worries about square roots of negatives. So this is, in fact, correct. But let's go through and illustrate the epsilon delta thing. So the instructions are find a delta greater than 0 that works for epsilon equals 1. I think that's the book's wording. That is, find a delta such that the inequality 0 less than absolute value of x minus 5 less than delta implies the absolute value of f of x minus L is less than epsilon. Well, f of x is square root of x minus 1. L, the limit, the rumored limit is 2. And we're taking epsilon to be 1. So we're illustrating how to find deltas for given epsilons. Of course, to actually prove something, and we'll do this shortly, you'd have to take an arbitrary epsilon and find a delta based on that. That's a bit more involved, but we'll illustrate that too. Okay, so here's the graph of the function. This was given in the question. Square root function, square root of x minus 1. It's an opening rightward semi-parabola. Of course, squaring functions are illustrated by parabolas, square root functions by parabolas as well. Well, half of parabolas oriented along the x-axis. So, in the notation given by the definition of limit, we have the f of x function is the square root function. The c value that x is approaching is 5. And we're claiming that the limit value L equals 2. So to get f of x minus L less than epsilon, or in this case, the square root of x minus 1 minus 2, absolute value of less than 1, this desired condition up here, we need the graph of y equals f of x to lie in the yellow band. Okay, we're claiming L equals 2, so here's the 2 along the y-axis. Epsilon equals 1 means we can go 1 unit up and 1 unit down from 2, creating this horizontal yellow band ranging from y value 1 to y value 3, centered about y value 2, the alleged limit value. Well, when is it that the function lies inside that yellow band? If I'm to believe the graph, then starting here, the function is within the yellow band and ending over here. That corresponds to input values of 2 to 10 along the x-axis. So if we input, if the graph is correct, an x value between 2 and 10 into this function, we get the function's graph to lie within the yellow band and the output values to lie between 1 and 3. So we need to input values between 2 and 10. But this limit thing is set up in such a way that we measure distances from 5. So how close to 5 do you have to be? Well, on the left side, we can go as far away from 5 as 3. 5 back to 2 is a distance of 3. On the right-hand side, we can actually go 5 units over, from 5 all the way over to 10. As long as x is between 2 and 10, we're good to go. But that's not the way we answer the question. The question is, how close to 5 will this condition guarantee that condition. That condition being the graph of the function lies in the yellow band. Well, we can go distance of 3 to the left, and let's go distance of 3 to the right. That keeps it symmetric as it demands. And sure, now if I draw a blue band centered at 5, 3 units to the left, 3 units to the right, we get the function values for those x values to lie inside the yellow band. We talked about it in terms of intersecting the sides of the little green box. It intersects the left side at the corner, and it intersects the right side of the little green box right there. So we're good to go. It doesn't intersect the top or the bottom of the green box. Well, it does down here at the corner, but we gave special dispensation for that. We're good enough. We've got the curve lying within the yellow band for these values. So we'll take delta equals 3. By taking delta equals 3, when we take x values satisfying the condition 0 is less than, absolute value of x minus 5 is less than 3, that means you're taking x values within this blue band, except for 5. We did exclude 5. It doesn't matter what happens at 5. We'll take x values lying in the horizontal blue band, and sure enough, the y values correspondingly will lie inside the yellow band. So we'll let the picture do the work on this one. We'll do these algebraically here shortly. So if we choose delta equals to 3, indeed, appropriate input values, those within a distance of 3, of 5, those between 2 and 8, if you like, implies output values within the yellow band. That is, within a distance epsilon equals 1 above and below the limit value 2. So the punchline was, let's take delta equal to 3. It produces this picture, and you get the kind of behavior that you need. Back to the notes. Okay, let's set up an algebraic way to do that. What if you don't have a graph of the function? Are you good at graphing? You'll be a lot better once you learn Calculus 1. That's one of the main applications of graphing. So the previous example shows how we can use a graph of a function to find the value delta for a given epsilon value that works, that satisfies the implication condition, given here at the top of the screen for that particular function. But graphing a function can be a challenge. That's one of the applications of calculus, is to make you better at graphing. Chapter 4, we'll look at applying calculus to graphing functions. So we're going to need a way that doesn't depend on the graph if we deal with more complicated functions. We won't deal with very complicated functions, but we need an algebraic way to deal with this that isn't so reliant on the graphs of functions. We need an algebraic way to find deltas. For a function f, which has a limit L at c, for a given epsilon greater than 0, we find a delta such that the implication we desire holds as follows. So here's a two-step process. By the way, the book writes it in the opposite order. They state it as a whenever. These mean the same thing. We've been saying I want the delta condition to imply the epsilon condition. They're saying we want the epsilon condition to hold whenever the delta condition holds. Well, it's the same thing. As you'll see when we do the computations, we more work in this direction. We start with this condition and then demonstrate that condition. That is, we suppose this and show that it implies that. And that's exactly how the logic works. I prefer this statement. You like this whenever deal. It means the same thing, logically equivalent. Okay, here's how we're going to algebraically find deltas. We'll solve the inequality f of x minus L, absolute value of is less than epsilon, to find an open interval AB containing point C on which the inequality holds for all x except for C, possibly. Here's what that means. Let's go back to the previous example. That's when we had the numbers 2 to 10. Between 2 and 10, we had the graph of the function lying inside the yellow band. So solving the inequality related to the epsilons and the function values produces an interval. In this example, it was the interval 2 to 10. Back to the notes. Then we'll find a value of delta that places the open interval c minus delta to c plus delta centered at c, right? It's got to be done in this symmetric way, centered at c, inside the interval a, b. And then we'll get the inequality to hold in that so-called delta interval. And that's the second thing we did, back to the previous exercise. We chose delta to be 3 because we could go as far as 3 to the left-hand side and as far as 3 to the right-hand side, and we're good to go. I get the graph of the curve to lie within that yellow band. And we'll work these in this way, choosing a smaller of the deltas on either side. And I could go further on the right and we'd still have the function lying inside the band. I can't go further to the left. If you go any further than that, you start getting values of the function that are outside of the yellow band, points on the curve that are outside the yellow band. So we're choosing these furthest we can go to the left and the right, and then picking the smaller of those two. I could go as far to the left as 3 units, as far to the right as 5 units, and choose the smaller of those two. We'll choose a minimum of those two, and that's how we'll choose the delta values. And that'll come out of the algebra. All right, and then we had the interval 2 to 8, which is an interval of center 5, c equals 5, and ranges delta units, delta equals 3 to the left, and delta equals 3 to the right, 3 units to the left and the right of value c. So there's a geometric picture of what we did. Now we're going to do that. We're going to do it algebraically. So it'll be first step, solve the inequality. Second step, choose a delta value. Let's do 2 of those. The first one being not quite as unmanageable as the second one. All right, so same thing we just did, except this time we're going to do it algebraically instead of looking at a graph. It's a similar function. It's a square root function. I suspect you can probably graph the square root of x minus 7. Okay, consider this as the function f of x. C equals 23, so x will approach 23. Epsilon equals 1, and L equals 4. Find an open interval about C on which the inequality f of x minus L in absolute value is less than epsilon holds. Okay, that was the first step. Then give a value of delta such that for all x satisfying the delta condition, 0 is less than the absolute value of x minus c is less than delta, implies that the inequality absolute value of f of x minus L is less than epsilon. All right, find all x that satisfy this condition first, and secondly, do that symmetry thing. See how far to the left you can go and how far to the right you can go, and choose the smaller of those two to represent delta. Okay. By the way, the domain of this function, x minus 7 square root of, is all x greater than or equal to 7. We can't take square roots of negatives. Come back and see me in complex variables, and we'll take square roots of negatives all you want. We'll do calculus with those functions. But in here, no square roots of negatives. So the domain is x greater than or equal to 7. This previous note had 2 steps. The first step is to do the first part of the problem. Solve the inequality f of x minus L, absolute value of less than epsilon. Solve that for x. Okay, our f of x is x minus 7 square root of. Our L value is 4, and our epsilon value is 1. So we want to take this inequality and solve it for x. Absolute value less than 1, this is equivalent to the inequality without the absolute values of, we still have an upper bound of 1. You drop the absolute values, take this upper bound, throw a negative sign on it, and put it on there as a lower bound. We need this quantity in the absolute values to be sandwiched between -1 and 1. Then its absolute value will definitely be less than 1. For more details, see Appendix A1, where they deal with inequalities involving absolute values. That's exactly what you get. rewrite the upper bound, put a negative sign on it, and make it a lower bound. When dealing with these kinds of inequalities, that's how you eliminate the absolute values. Okay, we're trying to solve for x and get a condition on x. So to get the x by itself, we'll look at the center part, and let's add 4 to each of the 3 pieces. Okay, adding 4, we'll have 4, -1 plus 4 yields 3. We added 4 to get rid of that, so that'll be gone in the center, and we add 4 to 1 to get 5. So the inequality has become this. We're trying to solve for x, so we need to square throughout. Okay, the squaring function is an increasing function. When we have positive inputs, it's a parabola. As long as we have positive inputs, it'll preserve the inequalities, and we do. 3 is positive, 5 is positive, and this thing, it's a square root, it's positive 2, and it's between that 3 and 5. So we can square each of these 3 pieces, and the inequality is preserved. That is, 3 squared is less than square root of x minus 7 quantity squared is less than 5 squared. Why'd we do the squaring? To get rid of the square root, because we're trying to solve for x. And that yields 3 squared is 9. The square root symbol's gone. We got an x minus 7 in the middle. 5 squared is 25. You want to solve for x? Add 7 to the 3 pieces. 7 plus 9, 16. X minus 7 plus 7 is just x. That's why we're adding 7. And 25 plus 7 is 32. So this inequality holds if and only if each of these were reversible steps. This, or this holds. So we need x to be between 16 and 32. In interval notation, we need to take x values in the interval 16 to 32, using the parentheses to indicate it's an open interval, not to be confused with a point 1632. So I'll be explicitly and put the verbiage in when there's a possibility of misunderstanding. And after all, they told us to find an open interval. So there's the open interval. I'll put my answers in little boxes as always, if that's meaningful. Next, we need to find the delta. Okay, so then the question's going to become, how far from, what's the C value? 23. How far from 23 can we go and still have this inequality hold? Well, I know that inequality holds on the interval from 16 to 32. 23 is somewhere inside that interval. Let's see how far from 23 we can go to get to 16 and to get to 32. The distance from C equals 23 to 16, it's a distance of 7. Take the difference. The distance from 23 to 32, that's 9. Also take the difference in the correct order to get a positive, or throw an absolute value on there because that's how we measure distances. So I can go 7 units to the left and 9 units to the right. Let's call those delta 1 and delta 2. Choose the smaller of them, just like we did in that previous example when we had a graph. So choose delta to be the smaller of these two, choose delta to be 7. That produces then the interval. See, we'll go 7 units from 23, we'll go back to 16, right, and over to 23 plus 7, over to 30. Yeah, well, that's a subset of the interval 16 to 32. On the interval 16 to 32, the inequality that we want holds. This is a subcollection of that, subset of that, so this inequality holds. So the algebra's already been checked. It's been checked above. This is the same thing we did in the picture in the previous one. We chose a wide interval on which the inequality held, and then we narrowed it a little bit to find a delta value to make it symmetric with respect to the value C. And sure enough, 16 to 30, right in the middle of that, what's the average of those two? 30 and 16 is 46. Half of that's 23. Yeah, C's right in the middle of that interval. Right, and that interval is 7 units to the left and 7 units to the right of the value C. Okay, let's do one. Fear not, Calculus 1 students. Now, let's do one that's a little bit harder. This one's tricky. Okay, so we're going to prove that the limit as x approaches 0 of the square root of 4 minus x equals 2. Okay, here's why this one's harder than the previous ones. They didn't tell us what epsilon is. So what is epsilon? I don't know, it's epsilon. It's greater than 0. Could be anything greater than 0. So I can't really put my finger on a numerical value for epsilon this time. It's okay. The manipulations are going to be the same. They're going to be a little more bulky because I don't know exactly what epsilon is. All right. First off, limits exist when functions are defined on open intervals about c, in this case 0, except possibly at 0 itself. This function f of x equals 4 minus x square root of. Is that defined on an open interval containing 0? Yeah, that's defined provided x is less than or equal to 4. Then we'll be taking square roots of positives and we're good to go. So how about the open interval negative infinity to 4? It's open because I've excluded the endpoint. It only has one endpoint and it's excluded. Yeah, that's an open interval. There you go. It's defined on that open interval and that contains 0. You don't like that, take something smaller, just as long as it contains 0 and it's an open interval. And it's not too big. Can't contain anything bigger than 4. All right. So indeed, the function's defined on an open interval containing 0, except possibly at 0 itself. Okay, it is defined at 0, but that doesn't matter. This is a limit question. So there's kind of what I was calling step 0. Now we'll let epsilon be greater than 0. All we got to do is find a delta. Okay, so the following computations will be finding a delta that works, just like we did in the previous examples. All right, let me put a little square bracket here and consider the following scratch work, I suppose. I'm trying to figure out what delta to use. This ain't part of the proof. We step aside and look for delta greater than 0 such that. So here's what we want. We want 0 less than x minus c absolute value of less than delta to imply absolute value of f of x minus L is less than epsilon. For us, c is 0. X approaches 0, so let's substitute that in. And then that simplifies down simply to the absolute value of x. So it could be worse. So we want 0 less than the absolute value of x less than delta to imply f of x is the 4 minus x square root of L. L is 2. Plug that in. So we want the absolute value of this to be less than epsilon. Epsilon, oi. I don't know exactly what epsilon is. I know it's positive, and that's it. Okay. So let's do the same thing we did in the previous one. Let's take this epsilon condition and see when it's satisfied. So same thing we did before. Only thing is, I don't know what number epsilon is. So we'll work with the letter epsilon. Okay, absolute value of f of x minus L is less than epsilon. That is the absolute value of 4 minus x square root of minus 2 less than epsilon. That's equivalent to, get rid of the absolute values. Rewrite the epsilon as an upper bound, eliminate the absolute values, put negative epsilon on the other side. That's how you get rid of absolute values in inequalities of this sort. Okay, so that produces this, and just as before, solve for x. So try to get x by itself. First thing we'll do is add 2 to each of those 3 pieces. Okay, add the 2, we get a 2 minus epsilon on the left, we get a 2 plus epsilon on the right, and this negative 2 will cancel with the added 2 to leave us with a square root part. Okay, so we're closer to having x by itself. It's kind of like solving for x. Let's square throughout. Squaring function is an increasing function when you have positive inputs, so it'll preserve inequalities. When we have positive inputs, all 3 of these things positive. 2 plus epsilon's positive because epsilon's positive. This thing's positive because, well, non-negative. This thing is non-negative because square roots are non-negative. Ooh, I don't know about this one. 2 minus epsilon, I need that to be positive, at least non-negative. We need epsilon to be less than 2. So let's temporarily and parenthetically impose a condition that epsilon is between 0 and 2. You know it has to be greater than 0. I'm saying, yeah, for this inequality to hold, we better have it less than 2. I could potentially have a very big negative number over here if I let epsilon just do any old thing it wants, and then I don't get the inequality preserved with the squaring function. So little disclaimer there on the epsilons. We'll take care of this later, so we'll come back to it. With that assumption, we've got positive number, less than positive number, less than positive number. Square all three of them, the inequalities are preserved. And that's how we get rid of the square root. So that's the reason we're squaring. Take 4 minus x square root of squared. That leaves you with 4 minus x. Left-hand side's 2 minus epsilon squared. FOIL it. You'll get 4 minus 4 epsilon plus epsilon squared. Right-hand side is 2 plus epsilon squared. FOIL it, you get 4 plus 4 epsilon plus epsilon squared. So the only difference is over here we got a minus 4 epsilon, and over here we got a plus 4 epsilon. All right, and we did that to get rid of the square root. Okay, we're trying to get x by itself. So how about we subtract 4 from each of these three pieces. You'll lose that 4, and that 4. All right, that'll leave us with negative 4 epsilon plus epsilon squared, right. Negative x in the middle, 4 epsilon plus epsilon squared on the right. Okay. Trying to get x by itself. We got negative x. Let's multiply through by negative 1. Okay, that'll reverse the inequalities. Multiply both sides of an inequality by negative, it reverses the inequality. Property of inequalities, you're familiar with this, see Appendix A1 if you need a review. Then, okay, so we'll pick up a negative over here, and then we'll have, just change the signs, we'll have positive 4 epsilon minus epsilon squared, 4 epsilon minus epsilon squared. The negative x will become just a regular x. And we'll pick up a negative on this. This will become negative 4 epsilon minus epsilon squared. Multiplied through by negative, reverse the inequalities. Let's rewrite that where it reads less than. So it's got the smaller numbers on the left and the larger numbers on the right. So let's see, let's write this first. I tell you what, let's factor the negative out as well. That'll give us negative 4 epsilon plus epsilon squared is less than x, and then we'll have this on the right-hand side, 4 epsilon minus epsilon squared. All right. So when does that inequality hold? When x is between here and here. So f of x minus L in absolute value is less than epsilon holds, provided the x values are in this open interval from here to there, under the condition that epsilon is between 0 and 2. And the idea is epsilon is small, so for big epsilons, I'm not particularly interested in what happens. We'll do the paperwork when it's time. But we do have a restriction of epsilon less than 2 at this stage. All right, so now we need to find the delta. We found the interval on which the inequality holds. So you take x values in here, then the graph of that function is going to lie inside the corresponding yellow band. That's what we found. Remember, we had it in the yellow band. Maybe we went not so far on the left and then kind of far on the right, but then we had to do some symmetry thing and choose a delta value. That's where we are. We found the big interval, A to B, it was called in that step 1 process. Here's A and here's B. Okay, now we need to find the delta. Does this interval contain 0? It'd be better, right? We're saying x is close to 0. Let's see, yeah, 4 epsilon plus epsilon squared, that's certainly positive and has a negative out front. So yeah, this side's negative. 4 epsilon minus epsilon squared, you sure that's positive? Yeah, remember epsilon is less than 2. Indeed, this is positive for those epsilon values. So yeah, the left side's negative, the right side's right endpoint is positive, so 0 is actually in that interval. How far is it from 0 to the left endpoint? I'd take the difference. We'd take 0 minus the left endpoint, so this would become positive. We get 4 epsilon plus epsilon squared. Let's call that delta 1. That's how far to the left you can go from 0. Notice it's positive, right? So be careful in the order of subtractions. And the distance from c equals 0 to the right-hand endpoint, 4 epsilon minus epsilon squared, it is 4 epsilon minus epsilon squared. Let's call that delta 2. All right, we need to choose the smaller of those two. We need to let delta be the smaller of delta 1 and delta 2. Can you tell which one's smaller? Sure can. Remember, epsilon's positive. Here we got 4 epsilon plus epsilon squared, and here we got 4 epsilon minus epsilon squared. Well, delta 2 is the smaller one. Okay, then choose delta equals delta 2 equals 4 epsilon minus epsilon squared. Oh yeah, and we need epsilon to be less than 2, or we got stuck somewhere up here when we squared things. End of scratch work. Sorry, the bottom's cut off there. There's what we need to choose delta to be. 4 epsilon minus epsilon squared. Okay, I call this scratch work. Let's continue on. We left off with let epsilon be greater than 0. All right, if epsilon's less than 2, which we needed to get that stuff to happen on the previous slide, then choose delta to be 4 epsilon minus epsilon squared. Notice, by the way, that is indeed positive. If epsilon's big, it's negative, and we got a problem. We'll take care of that soon. Okay, so step 0 is the function defined in an open interval containing 0. Yeah, we took care of that. Step 1, let epsilon be greater than 0. We got no control over that. Step 2, find a corresponding delta. This is a delta we're going to use. And it's going to work. We've already checked the algebra. That was scratch work, though. So let's write it out nice and clean and show that if we suppose 0 is less than x minus c is less than delta, then we'll get, and I see it in the shadows down here, the absolute value of f of x minus L is less than epsilon. We're doing the same computations we just did on the previous slide, but backwards. Okay, so they ought to work. There's still a little trick to it. Okay, so let's see, x minus c, absolute value of c is 0, so that reduces down to the absolute value of x. And what we're dealing with is the absolute value of x is less than 4 epsilon minus epsilon squared. How do you get rid of the absolute value? Drop the absolute value, keep the 4 epsilon minus epsilon squared on the upper bound, and take its negative as the lower bound. So negative 4 epsilon minus epsilon squared is the lower bound. All right, now we're doing what we did last time backwards. We're trying to take this x and turn it into f of x minus L. We're trying to turn it into the square root of 4 minus x minus 2. We're trying to turn it into this. Looks like it must work downstream somewhere. Okay, so keep that in mind. That's where we're going. We got nothing but an x. What's the first step you want to take? We get a negative in front of it. What's the second step you want to take? Get a 4 in front of that. What's the next step you want to take? Introduce a square root. And finally, do the subtraction of 2. So that's the plan. Okay, so we left off up here. We've got nothing but x sandwiched between these other two quantities. Okay, let's put the negative in first. That's what you said, wasn't it? Multiply through by negative. Okay, that reverses inequalities. All right, we got this negative out front. We can just drop that by introducing another negative. Leaves us with 4 epsilon minus epsilon squared. Reverse this inequality, greater than. On the x, you pick up a negative. Reverse the next inequality and introduce a negative here. So we'll have negative 4 epsilon minus epsilon squared. Negative 4 epsilon minus epsilon squared. Okay, let's write that instead of greater than or equal to is less than or equal to. Just write it in the opposite order. So we'll take the rightmost term and make it the leftmost term. Reverse the inequalities, otherwise rewrite things. All I did was reverse the order and the inequalities. To get this, I like seeing lesser numbers on the left and larger numbers on the right, just like they are on the real number line. So we got negative x, eh? We're going where? Trying to get a 4 minus x. Okay, let's add 4 to all 3 parts. Add 4 to all 3 pieces of the inequality. That doesn't change the greater than, less than stuff. That'll give us a 4. Distribute this negative. It was 4 epsilon, negative 4 epsilon plus epsilon squared. There's your negative 4 epsilon plus epsilon squared. 4 minus x. Yeah, that's the plan. Getting closer to f of x. And on the right-hand side, we'll have 4 plus Right-hand side, we had a 4 epsilon minus epsilon squared. 4 epsilon minus epsilon squared. Okay. Let's do the following. This is a real tricky part here. You would agree, parenthetic comment here, that 4 plus 4 epsilon minus epsilon squared is less than 4 plus 4 epsilon plus epsilon squared, wouldn't you? So we've got 4 plus 4 epsilon minus epsilon squared. Let's replace it with this larger thing. It's larger because, hey, here we got 4 plus 4 epsilon minus something. Here we got 4 plus 4 epsilon plus something. That one's bigger. So let's take this bound. I know this to be less than 4 plus 4 epsilon plus epsilon squared. So we're replacing that as an upper bound to get this thing. Here's why we did that. Now, what we're looking at then is a perfect square and a perfect square. We can factor this into 2 minus epsilon squared. We can factor this into 2 plus epsilon squared. How about that? 2 perfect squares. Now, this didn't totally come out of the blue because on the previous slide, we did something like that where we had perfect squares and then we took square roots. So we've done this before. It wasn't that much insight on my part, and I saw it in the scratch work. But you would agree with the validity of this. We can draw the conclusion of this inequality here. And I like that because now, hey, everything's positive. This is a square. We've said that 4 minus x has to be positive because we're in the domain of the function. Maybe eliminating the possibility that x is 4 if I say something like that. But we've got positive, positive, positive. How about non-negative, non-negative, non-negative? So we can take a square root of the 3. Square root function's an increasing function. That'll preserve inequalities as well. Take square roots of the 3 parts. The inequalities are preserved. The square root function is an increasing function. I'm depending on some of your knowledge from pre-calculus or high school. All right, the square root of something squared, that's the absolute value of the something. So this gives us absolute value of 2 minus epsilon, absolute value of 2 minus epsilon. Here we've got the square root of 4 minus x. Excellent, that's f of x, by the way. And over here, we've got the square root of something squared. Okay, that's the absolute value of the something. I can't just ignore those absolute values unless I happen to know that the something is positive, and it is in this case. 2 plus epsilon, well, certainly that's positive because epsilon is positive. So whatever this is bigger than 2, so it's certainly bigger than 0. 2 minus epsilon, remember we had the condition epsilon is less than 2. 2 minus epsilon then is positive if epsilon's that small. Also epsilon's positive, so this isn't, we're good, this is positive. And we can drop the absolute values. You can't just drop absolute values. You can drop absolute values when they're on positive quantities. And we checked, and they are positive things. So we can eliminate the absolute values because 2 minus epsilon is positive, and so is 2 plus epsilon. Okay, we're looking for f of x minus L. We got the f of x. We need to subtract 2. We need a minus 2 on this. So we'll subtract 2 from all 3 pieces. You'll lose this 2. You'll lose this 2 and pick up a minus 2 here, producing negative epsilon is less than square root of 4 minus x minus 2 less than epsilon. Okay, we've got this quantity sandwiched between epsilon and negative epsilon. That means the absolute value of this thing in the middle is bounded by epsilon, property of eliminating or introducing an absolute value and an inequality. Saying the absolute value of something is less than epsilon is equivalent to saying the something is less than epsilon and greater than negative epsilon, as we've done several times now. So we get something of this form. That's the reason we did what we did. This is f of x. This is allegedly L. We've got the absolute value of f of x minus L is less than epsilon. Excellent. We just showed the greatest hits are if 0 is less than absolute value of x minus c is less than delta, then absolute value of f of x minus L is less than epsilon. That's the very definition of limit with epsilons and deltas. Only little loose end we have is this only work for epsilon less than 2. That's good enough. But let's be mathematically moral about it. If epsilon's greater than or equal to 2, just choose delta to be 3. And that's what you'd get up here had epsilon been 1. If epsilon equals 1, and you plug that in here, you get 4 minus 1 equals 3. So here we're getting the same bound we would have had we used epsilon equals 1. The same computation going through with delta equals 3 will show that you get f of x minus L is less than 1. You've treated this as if epsilon were equal to 1. Same computation, you get less than 1. We're trying to show it's less than epsilon, and epsilon's what? 2 or bigger? Well, if it's less than 1, then it's certainly less than 2 or bigger. So the fact that f of x minus L in absolute value can be shown to be less than 1, then certainly it's less than 2, and 2 is less than or equal to epsilon. The thing to notice is f of x minus L in absolute value is less than epsilon. That's what you needed. So that takes care of that little loose end. And as far as epsilon delta proofs go, that's as bad as they get. So don't lose confidence just because this one was awfully involved and it had a trick or two in it. This is as bad as it gets in terms of epsilon delta computations. Back to the notes. Let's prove, okay, we've been using them, but we didn't have the background to prove theorem 2.1. The limit of the sum is the sum of the limits. Let's go back and prove that using epsilons and deltas. All right, this one might baffle you a little bit. It won't be as bad as that previous one though. Okay, so we're told that the limit as x approaches c of f of x equals L, and we're told the limit as x approaches c of g of x equals M. That means f is defined on an open interval containing c, except possibly it's c itself. It means g is defined on an open interval containing c, except possibly c itself. It means for all little positive numbers, I can choose a little delta such that I can make f of x close to L, you know. And similarly for the g function. So that's the hypotheses we have. We want to show, for any epsilon greater than 0, we can make f of x plus g of x within epsilon of L plus n. We've denoted those limits as L and M by making x sufficiently close to c. That is, we find a delta that'll work. Okay. For this one, let's do exactly that. Okay, first about the step 0 thing. We need to make sure the function is defined on an open interval containing 0. This function, f plus g. Because we're making a claim about the limit as x approaches c of f plus g of x. Well, first, we're told the limit as x approaches c of f of x and the limit as x approaches c of g of x exist. That means, well, that means they got to give us this. There's an open interval about c, call it the interval from a1 to b1, such that f is defined on the interval a1 to b1, except possibly at c. It's a limit. I don't know anything about what happens at x equals c. Also, similarly, for the g function, there's an open interval, say a2 to b2, such that g is defined on the interval from a2 to b2. It contains point c. G is maybe not defined at c itself, as always. Let's intersect those two intervals. C's in both of them, so C's in the intersection of them. Call the intersection the interval AB. And what A is the larger of A1 and A2. And what B is the smaller of B1 and B2, if you want an explicit version for it. Not necessary. We just need to show the existence of such an interval. But the interval obtained by intersecting these two is an open interval. The intersection of two open intervals, if non-empty, is an open interval. And both F and G are defined on the intersection of those two intervals, except possibly at C itself. So that's always going to remain a problem. And we've taken care of step 0. F plus G is defined on the interval from A to B, except possibly at C itself. Okay, that's the easy part. Now for the epsilon part. Let epsilon greater than 0 be given. Okay, they've told us two limits exist. So that means they've guaranteed the existence of two deltas. one for the f function and one for the g function. I want to consider the positive number epsilon over 2. If epsilon's greater than 0, then epsilon over 2 is greater than 0 too, ain't it? And the reason we're cutting it in half is we're going to add two things together. So that's why we're looking at epsilon over 2 at this stage. It'll be more apparent when we do the computations. But I want to say, hey, here's a little positive number. Then, since the limit as x approaches c of f of x equals L, there exists a delta 1 greater than 0 such that when the absolute value of x minus c is greater than 0 and less than delta 1, then f of x minus L is less than that little positive number. That little positive number I'm taking to be epsilon over 2. That's where the delta 1 comes from. We ain't got to find it because we're not showing the limit exists. They told us that limit exists. So we know a delta 1 exists such that blah, blah, blah. They also told us the limit as x approaches c of g of x equals m. Okay, so we don't have to find a delta 2. We just know one exists because we know the limit exists. Definitional limit. So next page, same thing, but for the g function. Similarly, since the limit as x approaches c of g of x equals m, there exists a delta 2 such that when the absolute value of x minus c is greater than 0 and less than delta 2, then the absolute value of g of x minus m is less than that little positive number. Let's use epsilon over 2 again. Choose. I choose my words carefully. I chose choose when we choose the delta. To emphasize, you got no control over the epsilons. The epsilon, they could be anything. But once you've given the epsilon, then you choose the delta, likely based on the epsilon, as we've done so many times in the examples from this section. This time we're choosing delta to be the smaller of these two deltas. Here's why. If 0 is less than the absolute value of x minus c is less than delta, then this absolute value of x minus c, it's less than delta 1 and it's less than delta 2 because it's less than the smaller of those two. So it's less than both of them. That means you can use this epsilon over 2 stuff that we had upstairs because absolute value of x minus c, it's less than delta 2. Okay, then we can use this epsilon 2 stuff. Previous slide, it's less than delta 1 as well. Well, you can use the epsilon over 2 stuff up there that related to f and L as well. So that's why we're choosing delta to be the smaller of those two. Now we want to consider f of x plus g of x minus L plus m. We're trying to show this function, the sum f plus g, has this limit, L plus m. So that's the thing to consider. We've got function minus limit value less than epsilon. So it looks like it's going to work. Well, we want to show something about f plus g. We know something about f and we know something about g. So let's separate them. I know f of x gets close to L. So let's rearrange this and associate f of x and the negative L and g of x and the negative m that comes from the distribution. So let's associate them like that. I know f of x gets close to L. I know g of x gets close to m. So this whole thing ought to get close to 0. Well, we can make it arbitrarily small. Let's use the triangle inequality for absolute values. The absolute value of the sum is less than or equal to the sum of the absolute values. See Appendix A1. If this sounds new to you, you should have been exposed to it somewhere in your travels. The absolute value of the sum is less than or equal to the sum of the absolute values, the triangle inequality. You ain't seen the last of it if you're taking more math classes either. You'll see triangle inequalities in your future for sure. So that allows us to break this up. It introduces an inequality. Hey, we know f of x minus L is less than epsilon over 2 when the absolute value of x minus c is less than delta 1. Well, it is less than delta 1 by our choice of delta. So we can put an epsilon over 2 there. We know g of x minus m in absolute value is less than epsilon over 2. Well, when the absolute value of x minus c is less than delta 2, and it is. It's sufficiently small, the absolute value of x minus c, so that it's less than both delta 1 and delta 2. they both hold. We can replace both of them with epsilons over 2. Add them together, you get epsilons. That's why we used epsilon over 2. And we've shown there exists a delta such that the absolute value of x minus c greater than 0, less than delta, implies this function minus that number is less than epsilon. And that's the very definition of the limit of that function equals that number. Looks a little bit different because we're adding things together here, but it's the same thing. It's the definition of limit with the epsilons and the deltas. Okay. So in terms of epsilon delta limits, I think that's it. What we're going to look at now is not the end of limits, but it's the end of these kinds of limits. We're going to look at what happens when a limit fails to exist. If we negate the definition of limit, say we want to show the limit as x approaches c of f of x is not L, then I got to take that for all epsilon greater than 0, there exists a delta greater than 0 such that this implies that. We got to negate that. I'll leave it to you to think this through. But what we would show is there's some epsilon greater than 0 instead of for all epsilon greater than 0, such that for all delta greater than 0, instead of there exists a delta greater than 0, there exists some x, instead of for all x satisfying something or other, some x satisfying 0 less than x minus c, absolute value of less than delta, and the absolute value of f of x minus L is not less than epsilon. It's greater than or equal to epsilon. So there's a bunch of negations going in there, but if you claim the limit as x approaches c of f of x doesn't equal L, that corresponds to this stuff here. What you're showing is there's a bad epsilon. That is, there's an epsilon for which there's bad x values, no matter how close you get to c. Bad. All right, so what we'll do is illustrate this with an example, and it'll be based largely on this idea here. So here's a graph of a function. It's got a gap in it. It's not a continuous function, whatever continuity means. We'll define that using limits, in fact. Section in chapter 2 sometime, I think it's section 2.6. That's certainly not a continuous function because it's got a gap in it. We're showing the limit isn't L, is the argument they're putting together here. And they're doing it by saying, okay, here's L. We're going to take an epsilon, this epsilon, wherever the distance from here to here is, go from L minus epsilon to L plus epsilon. So we went up and down from L, the distance epsilon, and we drew a yellow band. We've got x approaching c. Is there a problem? Yeah. For these delta that they've chosen, the graph of the function doesn't lie inside the yellow band. This part's below the yellow band down here, so that's bad. Well, maybe you ought to make delta smaller. Yeah, well, no matter how small you make delta, you're still going to have this little bit of the function down here that's not in the green box. It doesn't lie inside the yellow band. That violates the definition of limit. I need the function to lie inside the yellow band. I make epsilon bigger and it'll work. Yeah, but I got to be able to do this for all epsilon, including the really small ones. This doesn't work for this particular epsilon. Well, it doesn't look small, but for the sake of a picture that you can see, for this epsilon, no matter how small you make delta, you're going to have a piece of the function that isn't inside the little green box within the blue band. So the limit doesn't equal L. All right, so that's the spirit in which we approach the next problem, is to find an epsilon where when I draw the little yellow band in the corresponding green box, we get a problem. We get a piece of the function that's not inside the green box. Okay, so last example from this section says, with that argument above, consider this piecewise defined function. They've even given us a graph of it. We get y equals x squared when x is less than 2. Okay, it looks like they've taken the domain to be 0 and greater. We get a parabola over here, y equals x squared. At x equals 2, the function takes on the value 3. At 2, we get out the point 3, 2 comma 3. And for x greater than 2, the function's a constant function 2. So it comes in 3 pieces. By the way, there's just one function here. Right? That's not 3 functions or 2 functions. That's just one function. Its name is h. It comes in pieces. It comes in 2 or 3 pieces. If you count the point, it comes in 3 pieces. It's a piecewise defined function, but it's only one function. They want us to show the limit as x approaches 2. Yeah, that's where all the action is, because that's where it's got a gap in it and some other things going on with a point. Limit as x approaches 2 of h of x is not 4, is not 3, and is not 2. Okay, here's those y values, 4, 3, and 2. So they're taking an interest, it seems like, in this point, and this point. All right, so this is actually a pretty good question to illustrate what's going on with the definition of limit by dealing with the negation of the definition of limit. All right, part 1, we want to show the limit as x approaches 2 of h of x isn't 4. Well, inspired by that previous picture, I want to choose an epsilon value such that when I make a yellow horizontal band, there's always a piece of the function that's outside, no matter how close we get to 2. Well, it's got that big gap in it, so I say, let's take epsilon equal to 1. If I take epsilon equals to 1, we're trying to show the limit's not 4, so we'll go down from 4 to 3 and up from 4 to 5. So we're looking at a band that runs from 3 to 5, 1 unit above and below 4. Okay, now the idea is what we're going to do is get close to 2. We're going to go a little bit to the left of 2 and a little bit to the right of 2. So we're creating a little band, a blue band of width 2 delta, centered at 2. So we've gone from 2 minus delta to 2 plus delta. I made it narrow in my picture. The idea is I'm trying to make delta small, but no matter how small I make delta, I don't get that function to lie inside this yellow band because we always got a little piece of it down here that's outside the yellow band. So this is the bad stuff. No matter how's it described here? No matter how small delta is, the blue band and the yellow band intersect to give a little green box in such a way that there are function values outside of the green box. Yeah, it's these function values right here. Ooh, what about this single point here? I mean, that's right on the boundary of the yellow band. It is not in the yellow band, it's on the boundary of it. Remember, it's an open band. Here we've got a y value of 3, and in the yellow band, we've got y values strictly greater than 3. So that little point, that's the function value at 2. What about it? Yeah, what about it? We're talking about a limit as x approaches 2, so it doesn't matter what happens at 2. By the way, that's not in the band either, but that doesn't matter. It's this stuff over here, these x values that are close to 2 and bigger than 2 that produce these little function values right there that are not inside the green box. That's a problem. Could you make epsilon bigger and still have that problem? Yeah, I could drag the bottom of this box down a little bit further, this yellow band, drag this down a little bit further, and I'd still have this stuff outside. Now, if I drag it way down, then it would include this, and it's not a bad epsilon. We're trying to show the limit doesn't exist. We're looking for a bad epsilon. Epsilon equals 1 works. Actually, I could take epsilon up to 2, and it would still work in this case. How about the limit as x approaches 2 of h of x is not equal to 3? Okay, now we'll take a horizontal band centered at 3. Let's try epsilon equals 1 again. All right. No matter how small you make delta, we still got a problem. Okay, and it occurs on the boundary of the yellow band. So here we are, we're considering L equals 3, epsilon equals 1, I said. So we'll go 1 unit up and 1 unit down. This time we go from 2 to 4. We're centering it on 3. And let's see, how are we doing when we draw, for this delta value, we draw a corresponding little green box. You know, on the left-hand side, we're doing good. This function lies entirely inside the green box. For these associated input values, no problem. It's in the yellow band, it's between 2 and 4. for these input values to the left of 2. But for the input values to the right of 2, we got that same problem we had before. This little piece of the curve is not inside the yellow band. It's on the boundary of the band, but it's not in the band. Remember, in the yellow band, we have y coordinates that are strictly greater than 2 and strictly less than 4. That's the reason we've got dotted lines drawn up there. And along here, we've got y equals 2. They're not big enough to be inside the yellow band. They're on the yellow band's boundary, but they're not in the yellow band itself, and that's bad. If that bugs you, then make epsilon a little bit smaller. Make epsilon equal to half, and then they're definitely well outside of the yellow band. And then epsilon equals a half is bad. If 1 is bad, anything smaller than 1 and positive is also bad. But we've got these bad values here. Hey, at least we've got the value of the function inside the green box. And what does that tell you? Nothing. I don't care what happens at 2, because it's a limit. Doesn't matter what happens at 2. And it's the same little story. We've got points outside of the green box, if you want to explain it like that. Okay, we'll move down and try L equals 2 in part C. Okay, so now we're thinking about this little point here, L equals 2. So we'll go, let's say 1 unit above and 1 unit below. Now, no matter how small you make the little delta band, it's the usual story, you got some bad values. And this time it's over here. To the right of 2 and close to 2, actually to the right of 2, however far you want to go to the right, you don't have any problems. The graph of the function is going to lie inside the yellow band. But to the left, no matter how small you make delta, you're picking up a little piece of this curve up here that's above the green box, and that's a problem. Look, the curve goes outside the top of the green box, and it can't do that. I mean, it can touch it at a corner maybe, but it can't go out of the top or the bottom of the green box. This goes out of the top of the green box. These are bad values. These points don't lie inside the yellow band or inside the green box, if you like. And no matter how small you make delta, we'll still have these points over here. And a piece of it's in there, but a piece of it isn't, and that's the problem. Could you have made epsilon a little bit bigger and still have it bad? Yeah. If I made epsilon equal to 2, then we'd have the yellow band run from 0 up to 4. Well, if I made it 2, it would contain all of the curve then. On the left, we'd be okay. But anything less than 2 and you've got a problem. You'll have a little bit sticking out above. So we're looking for bad epsilons. Epsilon equals 1 works. Anything less than 2, in fact, will work as long as it's positive to give us those bad values outside of the yellow band. And of course, the idea is epsilon should be thought of as little. So to wrap up this section, the problem in the first one was we could have taken epsilon, I think I verbally said this, to be as big as 2, and we'd still have the bad values. We'd have these bad values over here. If we went a distance 2, they'd be on the boundary. If I took epsilon, it'd be larger. We talked about that. In this last one, any epsilon greater than or equal to 2 would not be bad. So if we choose an epsilon less than 2, then we're good to go to have the bad values. It's all about having the graph of the function inside that little yellow band, or more specifically, choosing the blue band and then therefore the green box, so that the graph lies inside the green box. Here we got a piece of it outside, no matter how narrow we make the thing. Here we got a piece of it outside, no matter how narrow we make the blue band. And over here on the top, we've got a piece outside the yellow band, outside the green box, no matter how small you make the little blue band. So there's how you negate the definition of limit. And trying to offer you some moral support here, this is as bad as it gets. Calculus is going to be a little bit more smooth sailing after we get through this formal definition of limit. We've spent, I don't know, hours on videos so far, and all we've got is limits set up, and a part of it was motivation, and another part of it was informal. Well, there's the formal definition of limit. You're welcome. It's a good thing we went through the informality, I think, in the previous section. We're going to see some other kinds of limits, and we're going to deal with them formally as well. They won't be quite as bad as what we've dealt with just now. There'll be a little bit of new stuff. When we get into chapter 3, things get a little more leveled out and a little more computational. In terms of test questions and so forth, we'll probably concentrate on more computational things as well. But the theory is a little part of it too. Finding deltas given epsilons is certainly it's a part of calculus 1. So have a nice day. Good to have this formal definition behind us. We'll continue on in section 2.4 next. I'll see you there soon. Bye-bye.